Hey everybody, this is Miss Eisencraft here with lesson 8, practice problem help from Algebra 1. Okay, so let's just jump right in. Priya is buying raisins and almonds to make trail mix. Almonds cost $5.20 a pound, raisins cost $2.75 a pound, and Priya spent $11.70. They give us this nice equation already, so I'm going to go ahead and jot it down over here. So I have 520. That's representing total spent on almonds. 275 times our total spent on raisins. 1170 is the total she spent altogether. So it looks like what's going to happen is they're going to keep asking us how many raisins did she buy, and they're going to give us different amounts of almonds to keep plugging in. Okay, so in this first one, let's just plug the first one in. The first scenario says what happens if she buys 2 pounds of almonds. Okay, we would plug the 2 in, and we would notice we have a bunch of math to do because we would have to do 520 times 2, subtract it from 1170, and then take that answer and divide it. So what they are hoping that you notice is instead of doing all that work every time, right? Instead of doing all that, since we are going to plug in a whole bunch of different amounts of almonds every time, instead of doing that, let's just see what happens if we isolate the raisins on its own right now. Like, how are we going to figure out how many pounds of raisins? So even if we don't know exactly how many almonds we bought, well, no, when we do figure out how many almonds they purchase, how many pounds, we are going to multiply it by 520 times, we're going to multiply the pounds of almonds times 520, and then we're going to subtract that from the total that they spent altogether. So we still can do that even if we don't know how many pounds of almonds. Just say, okay, when we know it, we're going to subtract that from 1170, right? 520 times the pounds of almonds, okay? And what will that will give us the amount that was spent on raisins. Now, so many times when we do something on both sides of an equation, we're used to getting a nice simplified number. We didn't. We got an expression. That's okay. 275 times R. The total spent on raisins is 1170 minus the total spent on almonds. Then once you figure that out, you will divide that answer by 275. So the pounds of raisins is going to be the total cost minus the amount spent on almonds, which again, we have to plug in and multiply it by 520, and then all of that will be divided by 275. This is a more efficient way to keep solving for the raisins. So let me show you what I'm talking about here when we use a calculator. So I can type this expression in, 1170, even if I don't know the amount of almonds yet. Just leave a parentheses. And then I'm going to hit divide. And actually, you guys, I'm going to go like this. I'm going to take all of this and make this my top fraction. Okay. I also could have grouped it and did divided, but I just like making it a fraction. 275, and I just use that A over B. Okay, so now instead of having to plug it in over here, do the math and do everything backwards, we can just insert the amount of almonds here, and all the math is on this side. And after we finish, or the calculator finishes calculating this, we will be left with a number that is the amount of raisins that can be purchased. So if 2 pounds of almonds are purchased, you plug a 2 in there, it does all the math for you. It multiplies it by 520, subtracts it from 1170, takes that and divides by 275. Yeah, less than a pound because you bought too many almonds. So it looks like around 0.47. Nearest hundredth is 2 decimals. So it looks like a little less than a half a pound you can purchase of raisins. Now it's saying, okay, let's get less almonds. Let's only buy 1.06 pounds. Well, now you can afford 2, or if she spent 1170, then that means she purchased 2.25 pounds of raisins. And even less almonds, 0.64 pounds of almonds, would mean she spent more on the raisins or purchase 3.04 pounds of raisins. And this last one says, what about A pounds of almonds? All that means is replace the number with just A so we could figure out anything. So that is just the formula. So if you want to figure out how many pounds of raisins she purchased, you would say, I need to take 1170 minus $5.20 times A pounds of almonds, and all of that. I have to use grouping symbols in Canvas because it doesn't have the fraction option. All of that divided by 275. So this problem was here to illustrate how rearranging, even though it's looks kind of messy at first, how rearranging and having like the raisins isolated here is helpful in doing a lot of calculations when you just want to figure out raisins. Okay, let's go on to number 2. Okay, here's a linear equation, 2x plus 4y minus 31 equals 123. We are going to solve for x and then solve for y. So we're basically rearranging the equation, okay, isolating x in the first one, getting x alone. And we're still keeping it equivalent, right? We're not changing the solutions, we're just changing the way it looks. Okay. All right, solving for x. I know if I can add 31 to both sides, that will kind of clean things up because the 31 is a nice just plain number that can get combined with the 123. 2x plus 4y equals 154. Okay, now I want to still get x alone. Okay, so I need to get rid of all of this. This is being added to this side, so I'm going to subtract it. Some of you might go, shouldn't you divide? You would divide if you wanted 4 and y to be, if you wanted to get y alone and move it away from 4. But you're trying to get this whole term away from 2x. So it was added, so you just think of it as a number, okay? So 2x is equal to 154 minus 4y. Those cannot go together. They are not like terms. And we're not accustomed to solving equations where this happens, but just leave it alone. Then we still need to get x alone, so the opposite of multiplying is dividing. You have to divide all of this by 2. Okay. So x is 154 minus 4y all over 2, and that's what we're going to write over here. 154 minus 4y. Boop. All divided by 2. I think that's gonna make sure I did that right. Yeah, that can be simplified, but we're going to leave it like that for now. Okay, next problem, or same problem, next part. Okay, let's solve for y now. So if we solve for y, we have 2x plus 4y minus 31. Same thing, adding 31 to both sides. This time, we would like to see the y isolated. So we are going to subtract 2x because this 2x is just a term out front. Think of it as just a number, okay? So 4y is 154 minus 2x. Those do not go together. Then divide by 4. And you have to divide the whole side by 4. So y is equal to 154 minus 2x all over 4. Yay! 154 minus 2x. We need all of that divided by 4, so you have to use grouping symbols. Fun. 3. Okay, a table. I love tables. A car traveled 180 miles at a constant rate. So it went a total distance of 180 miles. And it's saying it traveled like the same speed the whole time. Complete the table to show the rate at which the car was traveling if it completed the same distance in each number of hours. So we're using different scenarios. So if the car traveled 180 miles in 5 hours. How fast was it going? So 180 miles in 5 hours. You could just simply do the division. How fast was that? So you would take 180 divided by 5, 36 miles per hour. Okay, that would be the rate. So 186, that was the total miles. That is the total hours. And that would be 36 miles per hour. Okay, so that would go right there. The next one, well, what if this other car, a separate car, did the same thing, 180 miles, right? 180 miles. Come on, Mr. Penn, I believe in you. Let's go like this. 180, thank you, Mr. Penn, divided by 4.5. It only took 4.5 hours, so probably going faster. So if I took 180 divided by 4.5, I'm going to do it here on this calculator. So use my real calculator on the other one. It looks like it's going faster, which makes perfect sense. Because if it's taking you less time, you're traveling faster. Okay, I'm going to type that in at the end. 180 miles if another car is only taking 3 hours to go that total distance. Okay, I'm going to go ahead and replace this with a 3. That car is going 60 miles an hour. And the last one, 180 miles. This car, I don't think is following the speed limit. 2.25. Okay, I'm using my that car is traveling at a constant rate of 80 miles per hour. So I'm going to take these answers here. Okay. That car took less time, was only going 40 miles. This one was going 60. This one was going 80. So write an equation that would make it easy to find the rate at which the car was traveling in miles per hour, R. So R is the rate if traveled for T hours. So we actually basically did that. Every rate we took 180 divided by the time, 180 divided by the time, 180 divided by the time. And each time we got a different rate. So we already did that. We took 180 divided by the time, and we got the rate. And that was a really efficient way because we given time and we were calculating rate. So that is the equation I'm going to put here. 180 divided by time equals, I'm going to go like this just so it doesn't look like I'm dividing the denominator or the, I don't know, let's make it look a little cleaner. There we go. Okay, question 4. Clear all here. Boop. Clear all. All right, an easy one, I think. Bananas cost 50 cents each and apples cost $1 each. Select all combinations of bananas and apples that Elena could buy for exactly $3.50. So this is a good mental math problem, but I thought this would be a good opportunity to go back to writing equations. Bananas are 50 cents each, right? So the total you spend on bananas is 50 cents times B, okay? So this is an expression for total cost of bananas, okay? Apples are $1 each. So 1 times A, or just A, is an expression for how much you're spending on apples. And together you spent $3.50, okay? So the reason why this is nice is now instead of having to do all the mental math, I can use my calculator, even though these are pretty easy to do. 50 cents on each banana plus $1 on each apple. And we're looking for combinations that make $3.50. It looks like they're always giving it to us in the order of bananas and apples. So I don't have to be too careful. I can just plug in the first number in the first slot for bananas, the second one the next. I'll know it works if it equals $3.50 off to the right. Okay? 2 bananas. Oopsie. Just kidding. 2 bananas and 2 apples. Ooh, that makes $3. That first one does not work. We want 3.50. Next one, 3 bananas and 2 apples. Hey, that's a good one. 1 banana and 2 apples. Not enough. 1 banana and 3 apples. Also works. So having this equation here is nice, so I don't have to start over and calculate everything over. 5 bananas, 2 apples? Nope. How about 5 bananas and 1 apple? All right. Let's go back. Clear all. Let's keep on going. Okay. Next one here. I'm going to have to get rid of my calculator for this one. Okay. Okay, so we have a graph here. To grow properly, each tomato plant needs 1.5 square feet of soil, and each broccoli plant needs 2.25 square feet of soil. The graph shows the different combos of broccoli and tomato plants in an 18 square foot plot of soil. Okay, so we are going to do some pull down stuff here. So A is on the line. So let's interpret what it means. It's a solution, which means it must be taking up the 18 square feet of soil. So it works. So it looks like, according to the ordered pair, that there were 0 tomato plants and all broccoli. Okay, so let's pull that down. Point A is only broccoli was planted, but the plot is fully used and all plants can grow properly, meaning it used up the whole amount and didn't overcrowd. Okay. Point B, it looks like the 3 tomato and the 2 broccoli, it's under the line. So that tells me it's less, and there's going to be enough space, but there's still more room. So 3 tomato plants and 2 broccoli plants, but there's still extra space. C, 6 tomato and 4 broccoli properly took up all the space. 6 tomato and 4 broccoli, wrong one. 6 tomato, 4 broccoli, fully used. And the last one, 4 tomato and 6 broccoli, is off of the line. It's above it. It's overcrowding. It needs more soil. Boom. Question 6. All righty. Let's see if I can go back here. Oh my gosh, amazing. Okay, select all the equations that are equivalent. Oh, I don't even think we need the calculator for this business. So we could find the solution to this and see what other ones all have the same solution. But I also want to analyze what legal math moves were done. So we have 3x minus 4 equals 5. It appears as the first problem. Okay. Minus 4 equals 5. Oh, my pen's being weird. Okay, it looks like this first one, it looks like they added 4 to both sides. That's legal. 3x equals 9. Yay, that is an allowable math move. Yes, it is. Boom. This next one, if you look at it, they added 4, but then they didn't simplify or cross it out, and they added 4. They just haven't simplified it, but that is still an equivalent equation. Adding 4 to both sides, just attaching a +4 and a +4 is fine. They just wrote it out horizontally. It is good. This next one, it looks like they tried to take 3x minus 4 equals 5, and then here, they divided by 3, but that was not consistent all the way through, so these are not equal. No. No way. Okay. Does x equal 9? Well, I'm going to go from this one instead of the original. I know that 3x equals 9. And that cannot mean that x can also equal 9. That is not an equivalent equation, because you would divide by 3, x needs to equal 3, so no. Last one, it looks like they have -4 equals 5 minus 3x. Let's see if what did they do there? Let's just sort of inspect it. Okay, it looks like They moved this 3x. Now, the 3x look in front, it's positive. They took it away. That's legal as long as you also take it away over here. This 4 had a minus in front, so it assigns it a negative. Negative 4 is equal to 5 minus 3x. It's like rearranging. That is equivalent. It's weird, but it's equivalent. All right, last question. Han is solving an equation. He took steps that are acceptable. Good job, Han. But he ended up with equations that are clearly not true. Oh, no. Okay. So he moved the 2x and the 5. We didn't really show that a lot in middle school, but before you combine like terms, it's nice to put them next to each other, and that's legal to do with the commutative property, so that was fine. Then he blended the 7x and the minus 2x, or combined like terms. That's fine. Okay. But then all of a sudden, he subtracted 5x from both sides, and he got this false equation. Well, if you look right here, whenever you have variables on both sides and the coefficients match, okay, and then you have this other number, can 5x plus 6 ever equal 5x plus 5? No, because it's not possible. So when the coefficients match and then you're adding one number to this side and another number to this side and you have 5x on both, so we can conclude that Han didn't do anything incorrect. That false equation at the bottom is telling us there is no value of x that can make this equation true. It's unsolvable. Boop. All right. I know that was really long. Good luck. Thanks for listening.